everyone, welcome back to my math teaching online today. In this video today, I would like to show you how to do the iteration by substitution. And what do we mean substitution? So let me explain the concept a little bit before I show you the example. So you remember when you have a composite function in Math 12, which is you have an outer function and inside you have an inner function. So a function f of x of g of x. So the f of x is the outside function and g of x is inside the f of x function. And that you call a composite function. And that let's say your y function equal f of x, right? But your x here, f of x here, is a g of x, the inner function. And this we call a composite function, right? And you remember back in the first course when you do derivative, so therefore, if you take y prime, you take derivative, you have to use a chain rule, which is you will integrate the f of x function, the outer function first, right? The outer function first. Let's say the outer function like that. But also, you have to integrate time with the integration, the derivative, not integrate, but derivative of g prime of x, right? So that is the chain rule. We do that already. And this we call a chain rule. So the substitution method is the inverse of the derivative, which is we call an antiderivative. And the substitution is just the inverse of the reverse process of the chain rule in antiderivative of the chain rule, right? So now let's say if we call the function of f equal f prime here. Then we can rewrite this. We say if we want to go backwards, so this is if we go forward, right? Now if we go, the arrow go backward. So then it means we have to integrate this f prime function. Let's just put the same way, prime function, time with g prime of x. And we want this equal back to the f of g of x plus c. This is what we want to see, right? So let's just use this because sometimes we say, okay, if we let f of f equal f prime, so we can rewrite this actually, because in the textbook, I just want to write exactly in the textbook. They call this, let's call this f big f prime, here is the f. So they will write like this. And when we substitute, we'll say, let u equal g of x. So we replace this big function, we replace the inner function by the letter u. And then we make a new function, which is we call an f of u du. So we retain that the inner function here is a new function. And now we just integrate the f of u du in this form. Then we will have the back to the function, right? If we let u equal g of x. So actually, I should say, if u equal g of x, then we do this, right? Now it turned out this chunk here, we call it du. And this is the new u function, right? So that that's what it means, okay? And we call this is substitution because we substitute the g of x, the inner function, by letter u. Now, this sounds complicated, but if I show you the example, you will see it not so bad. So let's get right into the example, right? So, and then you will see what I mean. So let's say number one, if you have to integrate the function x squared minus 5, all of them to power 8, 2x dx. So now, using this technique, we will say we're going to let this big chunk here is, we call it u. So we say let u equal x squared minus 5. Then we do derivative, because remember we have to take derivative of this inner function, right? So we're going to take derivative of this inner function. So this, therefore, the derivative of it will be du over dx. And derivative of this is 2x and minus 0, right? But I don't have to put minus 0 here. Now, if I kick this dx up here, then I can write like this, and I can cancel this one. So it turned out du equal 2x dx. Now, if you look at this expression, 2x dx, 2x dx. So by doing this, we can replace this by du, right? And we can rewrite this as u to power 8, like that, because the whole thing here is u, du. Du is this expression, exactly this one, right? And exactly this one. So we replace this by the clean cut like this, okay? So now we will do the integration of this one, which is the antiderivative it, and everybody know how to do antiderivative now. So if the derivative means we take away 1 power, then anti we put it back 1 power. So the a here will become a 9 if we add 1 in power in here. But we also have to divide, right? So that will become 1 over 9 u to power 9 plus c. So this is we do the whole new derivative of the new function of u. But what happened? Let's see what happened when we plug it back. So this means that the u here is this big chunk here. So now after I do integration of the shortcut function, new function like this, now I substitute back. So I will have this equal 1 over 9, and the u now can substitute back into x squared minus 5 to power 9 plus c. So that's it. That is all it's about, right? So it sounds complicated when we explain, but when you're actually doing it, it's not too bad, okay? So that's the way it is. So we do number 1. Now we want to go to number 2. So let's say in number 2, you have to integrate x squared over 1 minus x to the power 3 dx. Again, this is very complicated if we don't use the substitution. So for this, we're going to say let u equal 1 minus x to the power 3. Then du over dx will be equal, now this will become 0, and this will become, we subtract 1 power, become 2. So that will become minus 2 x to the power 2 dx. So now you can see the pattern right here. The x squared dx is this big chunk on the top here, x squared dx. Except we have the extra minus 2, right? And this is also, actually this is at the bottom because we do this, right? So we kick the dx up here, so this is gone, right? So we have du equal minus 2x squared dx. Now we want just x squared dx. We don't want minus 2. So what do? We kick this back down here. So multiply become divide when we kick to the other side of the equation. So du divided by minus 2, and that gone. So now we're left with only x squared dx. So remember, this is fraction 1 over minus 2. And 1 over minus 2, we can bring it outside. So that's the constant, and we're allowed to bring it outside. So we can write like that, minus 1 over 2. And that will take care of that. And we just substitute, the top is 1, and the bottom is square root of u, right? Because we say this big chunk is u. And here we have x squared dx on the top. X squared dx become du. Now we can rewrite this as the rational power, which is u to the 1/2. But we're going to bring it up, so we can say minus 1/2 on top. And du, if we bring this up here, right? Because we rewrite this, become rational power, and everybody know about that. So that's all we have to do. Now I'm going to integrate this new function. So this will become minus 1/2, still minus 1/2. Now we add 1 into the power when we do antiderivative, so that will give us 1/2. So 1/2, but remember 1 divided by 1/2 will become 2. So this is already there. Now we have to time with 2. And and the top here, instead of minus 1/2, add 1 will be 1/2. And positive 1/2, right? So now, all what we have to do is substitute back. Now we can cancel the 2 down up here and the 2 down here. So that will become minus u to 1/2, but we can substitute the u. What is our u is this one, and that will become 1 minus x to the power 3 as c. That's all we have to do. So it turned out not too bad, right? If we do like that. So I guess that everybody clear now. Okay. So now I'm gonna go to the next question. Let's say if you integrate ln x over x. Now, the difficult part of this is sometimes we confuse. We don't know let u equal what. Do we let equal ln x or equal x? Usually we substitute u by a complex expression. So the ln x seems to be complex. Now, sometimes it's not quite like that, but most of the time. So by inspection, I just say let u equal ln x rather than just x, right? Because it sounds more complicated. So now I'm going to do derivative of this. Du over dx, right? Over dx, which is derivative, equal 1 over x. The derivative of ln x is 1 over x. If I kick the dx up here, I have 1 over x dx up there, and that down here is gone. So now you can see the pattern here. The 1 over x dx, which is this part, can replace by our du, because du equals that. So now we will substitute this ln x by u, and the whole thing here, 1 over x dx, will become our du. So now we just integrate this. Now this is power 1. So when you integrate, you add 1 more power, also become power 2. But you have to divide it by 2, and that is u2 plus c. Now you can substitute back 1/2, just 1/2. U is ln x, so we say ln x, and we have u square, it means ln x square plus c. And then we're done. That's it. Now, if we don't use the substitution, it's very hard because we have to do the chain rule backward. And that's why we use a technique like this to realize that, oh, we can do like this, and we don't. So this will be taken care of, like this chunk. When we do g prime of x, we do derivative, we take care of du. And you can see that when I take derivative, that is g prime of x is already taken care, and I change that become du right here. And what I do, I just integrate this one, and this one, it just automatically, because I make the inner function become u, and I take derivative of that, so that g prime of x right here. To see that, right? So that's the idea. Now I'm going to go to the next example. This is going to be hard. Sorry about this. I have to make a noise. I have to erase all of this part. Hopefully it's not so noisy. As I prefer that I can have a social interact with you rather than just on the computer, and I'm not so good at using the mouth and writing. I can practice that, but it takes longer and would rather concentrate into the content instead of practicing that. So some people are very good on the typing on the computer. Now my typing is not bad also. However, when it comes to math notation, and I have to write using the pen on the computer, it will be not comfortable very much for me. So I would to use a traditional like that. So sorry about that. I'm not quite a very advanced technology person, but at least I can use it a little bit, communicate with you and show you. Okay, so let me get back to the next question. So we have number 3, now we do number 4. So in number 4, now I'm talking about evaluate the iterate from 1 to 9, right? And we have a weird function is square root of x over square root of x. So now, you can say, okay, so what do we want to say? We say let u equal e to square root of x or just square root of x. Now in this case, I think that it's easy to say let u equal square root of x. And I change this become 1/2 rational power, x to the power 1/2. So when I do derivative du over dx, I got subtract 1 power, which is become minus 1/2, right? So this will bring it down minus 1/2, and this x become minus 1/2 power. But that's good because I can bring the x down here, and therefore, and let me pick the dx up here, okay? So now I have du equal minus 1 over 2, and I bring this down here, but I turn it back to the square root and dx. Now I know how to do it because I figure out the pattern here, right? Actually, sorry, I missed the ex here. The square root dx here at the bottom. And that's very matching with this expression. So I can replace the whole chunk of this expression here by du, because that is this. Du equal this. Except I got stuck with minus 1/2. But that is the constant. So it's easy to deal with it. Again, I can rewrite it outside minus 1/2. Exactly the way it is. And this is already a bottom, so I don't have to do anything. And what I do is just bring this outside, right? And 1 over square root of x dx. 1 over square root of x dx is just du. So I'm going to substitute here by e to the u. And this chunk here is like g prime of x we'll substitute by du. So now I just integrate the new function, and this already automatically take care because I take the derivative of this already. So now I turn just this big chunk here, right? 1 over x. 1 over x dx is 1 over x dx here. I substitute this here by this du because this one equal du, right? And minus 1/2, I just bring it outside. So this, I can substitute eu du. So now I can integrate the new function. And my new function is minus 1/2, just minus 1/2. Derivative or antiderivative eu, which is exactly e to the u plus c. Now I will substitute this by the right function. That will be e to the u. Instead of u, I say let u equal this. So now I substitute back. U is just this. Now I have to do integrate from 1 to 9. So now, this means I have to do FB minus FA, the lesson we learned previous, right, lesson. So now our function is this one, F, and the B here we substitute by 9, so that will equal minus 1/2 times with E to square root of 9, and minus exactly the same way, but minus with minus will become positive. So positive 1/2 e to the square root, instead of square root 9, now square root 1. And this will become minus 1/2 e to the 3, because square root 9 is 3, and square root 1 is just 1, and plus with 1/2 e square root of 1 is just 1, and I don't have to write 1. So that is our answer for this question 4. Okay, so now I'm going to go to the next question, which is question 5. Question 5, let's say I have to integrate pi over 6 to pi over 2, and cos of theta over sine 3, sine to power 3 theta, d theta. So again, I'm going to say let u equal the complicated one here. And actually, I don't have to write sine of 3 theta. I just say let u equal sine theta. And therefore, because I look at cos theta, d theta. So du over d theta will be equal, the derivative sine theta is cos theta. And I'm going to kick the d theta up here. And I cancel down here. So now I look at this, very clean, right? Cos theta d theta, cos theta d theta. So the whole expression on top here can substitute by du. And I'm going to rewrite this. And when I say u, I don't bother to put in the a and b here. The reason, because this is for sine theta. This is not for u function. So if you want to put in the border, the numerical of b and a here, you have to convert it into sine of u, not sine of theta. But because we just do the integration, so I don't bother to convert it, because after we done the integration, we're going to evaluate later, and when we substitute back, we allow to use back this numerical again, because that's for sine theta. So I skip the changing between the border, like the numerical when we convert into for u. But that's why I just say this one, I'm going to ignore it for now. I just pretend it's not there, okay? So I'm just saying, I'm going to substitute this by 1 on top. And down here will be u to power 3, right? Because that's the power 3. And du equal cos theta d theta. So I replace cos theta d theta by du here. Now, whether I put up top or I put right like that, it doesn't matter, it's the same, okay? Now I'm going to write this up here, bring it up here. So I'm going to change this become u to minus 3 on the top and du. Rewrite that. So now I'm going to have to erase the bars again. And this one will take time. This is the part I dislike it, right? Because it takes time. But if I use a computer, it takes even more longer because I don't use the mouse very fast. Okay. So now I'm going to integrate that. So integrate of that, I will add 1 power in here, minus 3 at 1 power become minus 2. And 1 divided by minus 2, it's just minus 1/2. U to minus 2 plus C. So now I'm going to substitute back, right? Before I substitute back, I'm going to bring this down, so I change it, become positive power. So that become minus 1 on top. And down here, it's 2u to power 2 plus c. Now it will be equal minus 1 on top. And down here is 2 and u square. I say let u inside theta, so now I put back psi, but u square, so it will be psi square theta plus c. And that is my answer. However, I'm not done yet, because now I have to evaluate back using this numerical value. After I substitute like this, I don't have to convert it back. You know, if I change the u here and change the number here for u, unless I do integrate u, but I ignore it for now, so it doesn't matter. So now we put it back. We're allowed to use the same numerical value, pi over 6 here and pi over 2 here. So now by doing that, I reduce the redundant work. Sometimes we still have to change between u if the expression is more complex, but that's not what I see here, right? So I'm going to just ignore this numerical value and turn it into the new function, just integrate the new function without evaluation. And now, after I substitute back, I use the same numerical to evaluate. So now I'm going to substitute back. So that will be FB minus FA, right? And now FB will be minus 1, 2 psi of pi over 2. And all of this will be square. Minus with minus, right? This is minus already, but when we subtract, we also have this, so that become adding. Adding 1 over 2 psi pi over 6. We substitute this and we square that. So now what this look like? Let's recall a little bit of trick. If you have an angle here, pi over 2, you see 90-degree angle, right? The same like pi over 2. The coordinate of this is 0 and 1. So the sine of pi over 2 is 1. So this is sine and this is cos. So sine of pi over 2 is 1. So this means this is minus 1 over 2 times with 1 square. So this is this. Adding. Now let's talk about the pi over 6. For the angle pi over 6, we refer back to the stencil triangle. So we have to have a little bit background trigonometric to do this kind of thing, right? So let's recall this for you. If we have an angle pi over 6, which is 30 degrees, and opposite with 30 degrees is 1, is 2, and this is square root 3. So opposite of 30 degrees, pi over 6 is 1, 2, sine is opposite over hypotenuse. So this value will be 1/2 square. And this turned out to be, minus 1/2, right? Because 1 squared is 1 times 2 is 2. This will be adding with 1 over 2 times with 1 over 4 when you square it. Now this cancel out with this. So it becomes minus 1/2, adding with 1 divided by 1 over 2. But 1 divided by 1 over 2 is reverse is 2. So this becomes 1.5. And that is, after we evaluate the interval, this is what we get for this question. So that is question 5. I'm going to go to the next question for you. So let me erase all of this again. Maybe I have to work it quicker. Let me just do this so it's really quicker. Okay. So now I'm going to go to the next question. And the next question is question 5, so now question 6. Question 6. Let me erase all of them so we have more. So for question 6, I have an interesting question, which is, let's say you have integrate dx on the top, down here, square root of 4 minus x squared. Okay, so you see, instead of put in the middle here, you can put on top the same, right? Now, what do we do with this? Do we use substitution or not? Now, the answer is no, you don't have to. And how do we realize? The only thing we realize quickly if we remember the formula. So at this level, sometimes it's a little bit tricky because if you don't remember the formula well, you might use another way around and take longer. Eventually, you still can get it. But some basic formula, you still need it, right? So in here, I write it down here for you. For the inverse trigonometric integration, we have a formula like this. If you have 1 over a squared plus x squared dx, actually I went through this with you in the first course already. Now it's just the reminding, right? So you have 1 over a squared plus x squared dx equal 1 over a 10 minus x divided by a plus c. Now x over a is just the angle, right? Notice this x here is the angle. Now, the next inverse function, if you see 1 over square root of a squared minus x squared dx, the answer of integration for this is sine. It's like r sine inverse of trig, with sine minus 1 on top. And the angle here is x divided by a plus c. If you have the dx on top over x, and then x squared minus a squared. The answer for this is 1 over a. Secants minus 1, the angle is x over a plus c. Now, it seemed to be a little bit complicated, but actually not quite, because they look very much similar. So as long as you remember one, you can relate it to the next one. Just, you have to pay attention a little bit, like you say, how do I know which one is tan, which one is sine, which one is secant, right? Just look at the pattern. If you don't have square root, right, then that is for tan, the inverse of tan. If you have a square root, you will have the inverse of sine and cos. And remember, in the previous course, I told you, if you have a derivative, if you have antiderivative 1 over 1 minus x squared, that antiderivative of this is sine minus 1x. If this is the case. Now, if you have a negative, then instead of sine, it will become cos. If this is negative, everything is exactly the same. Now, in the previous, we're talking about the numerical here, value here is 1. But now we go one more further, more advanced. We change this numerical value in terms of a squared instead of just number 1. So maybe it would be 5 squared, or maybe it would be 4 squared, whatever it is, right? So we apply the formula, is a lot easier. So now let's do this one and using the formula. So now if you look at here, what pattern it look like? Does it look like sine here, or tan here, or secant? And of course, it looks like sine, right? This is your a squared, and this is your x squared. So look at this formula right here, right? The one with the asterisk, I put it here. So now we know this will be just exactly the same, except our angle, the a here is a little bit different, right? The a here is, instead of 1, it will be 4, which is the a squared. It's 4. So we can change this become 2 squared. So now 2 squared is the same like a squared. So now we know the answer of this will be just sine inverse of sine, and our angle is x over a, and our a is 2, right? Remember, this is square, but when we take into the angle, it's just the numerical a, right? Not a squared. So it's 2. So the angle is x over 2 plus c. And that's it. That's how you do the iteration for this question. If you apply the formula, it's very easy. Now, let's do for a next question. A little bit more complicated and see how we do with that. Let's say you have dx. All of that over square root of 25 minus 16x squared. So this is very much like this, right? Except you can change this, become 5 squared minus 4x, and all of this squared. So now we know our a is 5, and our x is 4x. But the problem with this is because we have an x is 4x, so we have to take care of the numerical value here. Now for a, it doesn't matter. For this numerical value, we just apply the formula and just put over 5 instead of over 2 like that. We put over 5, this angle, x over 5. But what about number 4 here? So let's substitute this a little bit, okay? So let's do like this. Say let u equal 4x. Let u equal 4x. So du over dx will be equal to 4. And I'm going to pick this up. So du will be equal to 4 dx. So now I already take care of this expression. Dx become du. If I just replace the u by a little thing here so that I can take care. So now we start with the 4. So how do we solve for dx? To solve for dx, you pick the number 4 down here and cancel that. So basically 1 over 4 du equal dx. And now the 1 over 4, we can bring it outside and it below level, right? Remember. So the 1 over 4 here is like this. You can bring outside like that. And here you can just write du, right? And then down here it's just 5 squared minus 4x is u, right? So you can write like that. So now when you do this, we refer back to the pattern of this formula. This is our a square. This is our angle on x squared. Except we change the x become a u, but everything is exactly the same. So integrate this one, it will be equal to 1 over 4 times with sine minus 1 inverse of sine minus 1. Our angle will be u over a. And our a is just 5, right? Just that number. Plus c. Now we can substitute back. Equal 1 over 4 sine of minus 1 on top. And u over 5, you can turn back into u is 4x, right? So 4x on the top. And down here still 5 plus c. So that is our answer for the question 7. And I will give you one more question and then I will end this video here. Okay, so let's see what question I can give you. The last question I would like to give you will be the question A. Question. This is the last question. This looks complicated, but actually if we use substitution, it's very easy. So let me show you the last question, and then this video is really long already. I'm going to end it for this question. So how do we substitute this? We say let's u equal 1 plus 1 over x, a big chunk here, right? So now we say du over dx will be equal derivative of 1, 0, and derivative of this one, if you use the quotient rule, it equals minus 1 over x squared. If you use the quotient rule. So if you forget, you can go back and then try it and you will get the answer exactly like that, okay? So now I'm going to kick the dx up here and I cancel down here. So now, if you look at this, what does it look like? This here and this here, right? X squared dx, x squared dx. So now I can substitute this by u, but when I substitute u, be careful, right? Don't do this numerical value, because unless we change it for u, otherwise just say for now, let's ignore this, right? Ignore this for now. That's a quick way of doing it. So I want to say I substitute the top is u and 2 power 5. And the x squared and dx here, we can substitute by, make sure you have a minus. So I can put the minus outside, right? So x squared dx will substitute this by du. That's it. We don't have to do anything else. So now this turn out to be integrate. This will become 1 over 6 minus 1 over 6 u to the power 6. We add 1 power in here. Let's see. So now let's substitute back for the u. U is this big chunk here. 1 adding with 1 over x. All of this to power 6. And the c, we don't have to do c. And we go from 1/2 to 1. So now what this will become? This will become, okay, let's do it here. Minus 1 over 6. And 1 is just 1. Adding 1 over x, right? That's u, yeah. So adding with 1, and we substitute the x by number 1. And all of this power 6. And minus right? Minus become plus. 1 over 6. 1 and 1 over 1/2 to the power 6. So let's evaluate this. Minus 1, 6. 1 over 1 is just 1. So 1 at 1 is just 2. 2 to the power 6. Adding with 1 over 6. And this 1 is 1 over 1/2. 1 over 1/2 is 2. 2 at 1 is 3. 3 to the power 6. So basically, this will become minus 1 over 6 times with 2 to the power 6 is 64. Adding with 1 over 6. And 3 to the power 6 is, I think, 729. Let's see. 3 to the power 6. Yeah, 729. So now you can join in one fraction because that is minus 64 on the top, the same denominator, right? Adding with 729 all of this over 6. So what this number turn out to be? Minus 64, 665 over 6. And 665 divided by 6 equal 110.83 with the bar on top. So that's how we evaluate the last question. So, okay, turn over. So you will see that if we use the substitution method, it makes our task a lot easier, right? And that's why we call it mathematical technique. Sometimes we still have to practice a lot to see the pattern, but actually some questions are not so bad. Anyway, so now you understand the lesson. You understand what the substitution means and how do we iterate using the substitution. So I'm going to end the video, this long video now today, and I will see you in the next video. And in the next video, I think that probably we will go into the next lesson, which is iteration by parts. And that will be more interesting. And if you look at my website, I just remind you a little bit, go to mymathsteaching.ca, just type in Google mymathsteaching.ca. We see my beautiful website over there. And you can, see some of my video over there. If you're not interested in the whole thing, in the whole lesson, if you're not registered into my course, the whole course, then you can check my website. Okay, so Thank you for watching, everyone. Bye for now. See you. Stay tuned for the next video.